All right, hopefully the recording has started. Welcome to phase 4, everybody. Quick reminders, don't forget to book your project reviews. There's still a few of you who haven't done so yet. So just book your project reviews with me. If you've already presented on Friday, just a regular one-on-one slot will be good enough. Also start thinking about your third blog. Try and get that done within the next couple of weeks. But I wanted to give you all a rundown of phase 4 before we begin. So on the home run, I've updated our home run with the topic breakdowns for this week. But I want to start with talking about what the project's going to look like. So this project is going to be quite different from our last two. Yes, it is still machine learning, but you will get the choice of one of 4 topics. The 4 topics being time series analysis, a recommendation system, image classification, or natural language processing. And the natural language processing is also a classification problem. So if you're immediately drawn to one of these, great. If not, just work your way through the phase and then you can pick one. I'm going to talk about these in more detail, of course, over the course of the phase. But also now is a really good time to start thinking about what you want your capstone to be, because the phase 4 project can either complement your capstone or be something that your capstone is built off of. So these topics are kind of like electives. So really good idea to start thinking about it. Happy to talk through any ideas that you have during our one-on-ones. But to start, this week is going to be a little bit all over the place. Today and tomorrow, we'll be talking about 2 unsupervised learning techniques that are pretty prevalent in the machine learning space. Of course, there are not just these 2, but I'll mention all of the ones as we go through it. On Thursday, we'll be talking about big data. Now, my study group of big data is going to be very, very high level. Honestly, not many students right out of boot camp will start working with big data, but I will set the stage as to like when you might end up using big data, things like that. And then on Friday, we'll hit recommendation systems, which is one of the first 4 main electives. Also to preface, next week we're going to be doing 2 sessions of natural language processing, even though it's one topic, because I will be talking about one of the appendix topics. And then also, just to show you all the very end of phase 4, there is a topic called operationalizing code with AWS. I will not be doing a study group on that topic because if you go onto those labs, you'll see that it actually links to an AWS tutorial. Instead, what I'll be doing is during the capstone phase, I'll be talking about specific AWS applications that you might incorporate into your project. So this is more for like doing a Jupyter notebook on AWS. I'll be talking about how you can set up a database or run a model off of AWS. So just to kind of set the stage for what phase 4 is going to look like. But yeah, I will not be giving out the project as early this time because we do have to make our way through all of these different topics. And so the project will truly be a 1-week project. So I am planning to group you all up. So at some point, probably towards the end of next week or beginning of week 3, I'll send out a poll for you to indicate what kind of project you want to work on, and I'll group you all based on that. I do want this project to be a very quick, chill project, just so that you lead into your capstone very smoothly. All right, any questions about the overview of phase 4 before we begin? Great, well, if anyone has any questions later, feel free to let me know. All right, so that's an overview of phase 4. Today, we're going to be starting with PCA, which stands for Principal Component Analysis. Part of today, what we'll be talking about, this is not a long slideshow, but it's a lot of conceptual understanding. We're going to talk about unsupervised learning and what PCA is, why we got to do PCA, how it works, and how we evaluate. So to start, unsupervised learning. So far, phases 2 and 3, we've been doing supervised learning because we're trying to predict something. Usually, when we talk about supervised learning, our training data is supplied with labels. That's why, we're predicting a target. We have a target variable of the price of a house or a target variable of whatever you're classifying. Those are all targets. So supervised learning is done to predict unlabeled data. Now, unsupervised learning, there are no labels. So today and tomorrow, today we're talking about PCA, tomorrow we'll actually be talking about clustering. Then in NLP, I'll talk about this thing called LDA, also kind of similar, also unsupervised learning. But you'll see that with these, with unsupervised learning, there are no labels involved. So I'm not going to be going through any code today, but tomorrow we will. But one example of unsupervised learning, I'll give a clustering example really quick. I've given this example a couple times before. One of the most common applications of doing unsupervised learning is clustering. And an example I like to give is basketball. So in basketball, we have the 5 positions on the court, but people are saying, sports researchers are saying that maybe there's a better way to group players than these 5 positions. Like maybe you want to have more granularity, maybe you want to have like 7 to 10 different positions, and then you play whoever you need to, or you want to have fewer categorizations. So clustering is one method that you can use to mathematically create these groups without any labels. So it's basically doing these groups based on the features of players. We'll explore clustering more tomorrow. Now, PCA is a method of dimensionality reduction. So PCA stands for Principal Components Analysis, and it's unsupervised because we're only telling it how many dimensions to reduce to. So where would you use dimensionality reduction? We'll actually talk about that on the next slide. Let's just say you have 100 features, 100 X columns in your data, and it's taking your model very, very long to, train on this data. Let's just say really quickly, for computational efficiency, you want to drop it down to 10 features just to see if your modeling is actually working or not. Instead of dropping like 90 of your features, you can run PCA and it'll basically condense your feature set from 100 to 10 features. So you can tell it, all right, I want 10 dimensions for my feature space, and it will do that. So PCA will reduce the dimensionality of the feature set into n principal components while maintaining its variance. Now that I'll talk about in a little bit as well. And what each principal component will be, it'll be a linear combination of your original features. So for example, if we're taking the Syriatel data set, for example, I think that data set had roughly 20 or so features. And let's say you want to just lower it down to 3. So you'll have feature 1, 2, and 3. And each of those features will be a linear combination of your other features. So maybe principal component number 1, and each of these resulting new dimensions will be called a principal component. Maybe principal component number 1 will be like 0.5 times number of minutes used plus 0.2 times international minutes, or it can be like 5 times, what's another one? 5 times your number of texts, for example. So that's what it means by a linear combination. So each of these principal components will be a linear combination of your original features. Now that's very important to know, so that if you wanted to analyze your principal components, you can actually extract information like that. All right, so we're going to talk about the curse of dimensionality next. So why and when do we use PCA? As we have more features, the data points naturally just become more sparse. Imagine if you're doing anything from 2D and you scale it up to 3D, the overall distance between your points will end up being larger because there are just more dimensions. Of course, we can only think about 2 and 3D because that's all we can perceive, but this does scale up. When you have, and actually when we get to later topics this phase, when you deal with natural language processing, we sort of had a sneak preview of that. Your feature space will be as large as the number of unique words you have. So if in your data you have like 5,000 unique words, you're going to have 5,000 columns of data. So that data is going to be very, very sparse, very similar to even image data, which we'll hit later this phase as well. So as the distance between points gets greater, it makes it more and more difficult to implement machine learning models, not just through time complexity, but also through computational complexity. You've imagined the processes of gradient descent, you're going to have to be doing that on way more features as you increase the number of features, and that's going to take much and much longer. So it's important to think about time and space complexity, not just, the number of features that you have, but also how long your models will take to run. And sometimes it does actually become a cost in a lot of big companies when you're implementing very, very large machine learning models. Sometimes you only have a certain amount of computational power. Back in the day, you used to have to wait to implement like a really large machine learning model because there's only a certain number of servers in a room. But now you actually are paying for cloud computing. And so the amount of power that you use, it's important to make sure that you're using it efficiently. In like a really big data space, you can't just freely, let's test 10 of these models, see how they work. Maybe you only have enough to test like 2 or 3. Really depends on how large your models are. Okay. Curse of dimensionality is a very big thing that people think about when you're talking about, especially big data, when you get more into more in-depth machine learning. So good to think about. So when do you want to use PCA? So PCA specifically is useful when you have a lot of continuous features, and we'll see why that is in terms of the math of how it's computed. And it's also best for clustering or for computationally heavy machine learning algorithms like SVM. So SVM, we talked about that at the end of last phase, works very, very well with PCA. PCA is an algorithm that actually optimizes for variance. Another way you can think about variance is separability, which we mentioned at the end of last phase. And so PCA is going to reduce your dimensionality while retaining separability. So if you can imagine SVM, which is the model that it tries to separate your data with like a hyperplane, it overall makes it more efficient because with SVM you're going to have to do the kernel trick as well. If you're doing the kernel trick on fewer features, it's going to be more efficient than already doing the kernel trick on like already 100 features, so it's going to make it a lot more efficient. So typically when you're doing SVM, when you have more than like 50 features, you naturally will want to use PCA already. Cool. At this point, thoughts or questions? Okay. So PCA mathematically is quite complicated. It is fully a linear algebra approach. So mathematically, principal components are found through doing the eigen decomposition of the covariance matrix. Now we know what the covariance matrix is. If you do like df.core and you get the correlation between every feature every feature and every other feature, that is correlation matrix, but covariance matrix is very similar. Covariance matrix is that but not normalized. And you're basically decomposing that matrix. Now, eigen decomposition is a process that we don't need to talk about at all. It's not super important for us to understand at this moment, but eigen decomposition helps us understand in our covariance matrix what patterns or what relationships are prevalent. And so it tries to maximize the variance of your data because we find that through our eigen decomposition. You can actually walk through this process in one of the labs, but I don't think it's super, super important for us to understand PCA. So just very, very briefly, how the process of PCA works. You first have to recenter your data such that the means of each feature end up being 0. Sort of like standard scaling, but without dividing by your standard deviation. Next, you're going to get your covariance matrix, which is very, very similar to df.core. Then you're getting your eigenvectors of your covariance matrix. Now, just a kind of not super important to know, but eigenvectors, basically, if you think about n-dimensional space, eigenvectors are always perpendicular to each other. So that just reduces the redundancy in your covariance matrix. I do think that that's not an important concept for you all to understand at this point, but you can get your eigenvectors, which is basically the covariance matrix, but reduced redundancy. You can sort it, and then you're multiplying your eigenvectors by your recentered data to actually get your principal components. So your principal components are basically scaled versions of your eigenvectors scaled by your features. Again, in one of your labs, it actually walks through the process of doing this. But this math, it's actually doing a process known as singular value decomposition, which is a completely linear algebra process. Not super important to know for now, but if you ever come across the acronym like SVD, that's what's being done for PCA. Cool. Questions about this? This is a very mathy slide. If this is all like going over your heads, that's completely okay for now.
What did you say SVD stood?
SVD stands for singular value decomposition. Let me see, actually, if I do singular value decomposition, it is a very mathematical term, and the whole idea of doing singular value decomposition, let me see if there, oops, I want to see some images. It's basically, okay, this is kind of like SVD. Decomposition is they're taking your covariance matrix and they are separating it into 3 different component matrices. What this is, it's not important right now, but it is a mathematical process, and you're basically doing this decomposition on your covariance matrix. And then where you get your principal components is actually out of this matrix over here. All these mathematical terms, not important. I'll tell you, SVD comes like at the very end of a linear algebra course in college for like pure math. So not important for us to understand right now, but just know that it's extracting non-redundant information from your covariance matrix. But yeah, if you ever were to like read any of the machine learning books, they will mention SVD very likely. Cool. Any other questions at this point? All right. Okay, so use cases of PCA, and I do want to talk about some PCA alternatives as well. Let's see, my computer lagging out. Okay, so one easy way that you can use PCA is actually for visualization, or actually dimensionality reduction for visualization. So this is an example of actually one of the 3D scatter plots that I've done for one of my projects. I actually did this for my classification project. And if you just want to visualize the separability, remember I talked about this last time, if you want to visualize the overall separability of your data, you can do this by first taking your however many dimensions of data that you have, reduce it to 2 or 3D, plot it on a graph. And just like that, of course, you'll never see it perfectly separable because you are compressing something from like however many dimensions down to 2 or 3. But if you can sort of see that distinctly, the different color points are moving different ways or are scattered in slightly different ways, that is a sign of separability. This is not the best, not the best screenshot that I have, but when I plotted this in Plotly, you can actually drag and rotate your 3D scatter plot. You could actually see that the blue points and the red points are kind of separable. And this is, I think I took like over 1,000 dimensions of data and compressed it down to 2 or 3, which is why the shape is a little weird. But essentially, PCA or dimensionality reduction as a whole can be used to lower dimensionality for visualization purposes. Now, the bulk of your content focuses on PCA, which is, I would say, the most commonly used dimensionality reduction tool, mainly because PCA tries to maximize or optimize for variance in your data, such that if you had like a feature that doesn't vary at all, let's just say maybe you have like a dummy variable of, let's say you have, in your housing prices, you had waterfront as a variable, but only like 5 out of like 20,000 of your houses has a waterfront. That feature will be less important in PCA. So the waterfront component of your principal components will be a lot smaller than something that varies a lot. So maybe like square footage has a lot of variation in its values. Square footage will likely be a greater component of your principal components. So that's how you understand, the variation in your data or the separability of your data. All right, so there are several different methods. So first PCA, and I do want to pull up this documentation real quick so we can take a look. The way that you implement PCA, very similar kind of to like a scalar. It is used as one of the steps. You can use it as one of your steps in your pipeline. It is a pre-processing step that you could use before throwing your data into a model. So technically for this last project that you all did, if you had a lot of columns, maybe something you do is explore whether PCA will help your model, maybe in terms of time that it takes, or maybe in terms of reducing some redundancy, you can do that too. But how you use it, pretty much the only parameter that you have to set is n components. So let me see if they have an example here. There we go. So here you can see that we are instantiating PCA with n component equal to 2. Same thing, you're doing dot fit. There's also fit transform to transform your data from however many dimensions down to 2. There's also dot transform. So you should only do PCA fit transform on your train set, transform on your test set. Same with like all the scalars and all the other pre-processing steps that we talked about. Also, you can inverse transform. So if you have some, I don't know, let's say you wanted to take a look at your data points, or if you have any results from coefficients, you can actually employ reverse transform or inverse transform on your data. Something else I want to talk about is, one downside of doing any sort of dimensionality reduction is you do lose interpretability. So for example, if you were to run a random forest model, for example, and you had 1,000 features and you do feature importances, you can take a look to see what the important features are. However, if you're doing PCA first, and let's say you lower it down to 10 features and you have your feature importances and it shows you that 5 features are more important, you would have to do another layer of figuring out what the important features are, because your important features will just be PC or principal component 1, 2, 3, 4, 5. And then the way that you look for that is through one of the attributes called, I think it is N, no, which one is it? Oh, here, components. Yeah, it would be components. So with each component, you can actually see the linear breakdown of each of your original features. I think it is. Let me double check real quick. Yeah, I do think it is out of components.
You don't have
yeah.
to do the reverse inverse first in order to see it.
So they're kind of different things. The first one, if you were to do inverse transform, it takes like your 10 dimensions and re-blows it up to 100. If looking at the, what was the one that I was just talking about? What's it called? If you're looking at components, it will literally tell you, okay, PC1 is made out of like what proportion of each of your original features. So they're kind of different.
Got it.
Yeah,
Thank
that's
you.
a good clarifying question. You're welcome. Cool. Let me think if there's, I don't think there's anything else that's big about implementation, but any questions at this point before I talk about some of the other methods of dimensionality reduction that you might use? Nice. Okay. So back to this, PCA is good for dense continuous data. Another dimensionality reduction method that if your data is more on the sparse side, so if you had NLP data, so if you had a lot of word data, like what we were doing with naive Bayes, truncated SVD might be a little bit better. It's actually more efficient because if you have a lot of zeros in your data set, truncated SVD works a little bit faster. And then also there's another one called TSNE. TSNE is a neat one. And actually all of their, if you look into all of their documentation, the way that you employ them is exactly the same. So actually, let me open this one as well. The main thing that you want to give it is the end components. So this is truncated SVD. You can see that it works with sparse matrices efficiently. That's nice. Okay. And then the other one I wanted to talk about was TSNE. So TSNE is a good one if you want to visualize your data, because whereas PCA and truncated SVD, they optimize on variance. TSNE optimizes for separability. So if you ever wanted to just visualize your data, TSNE would usually give you better separation in your data points when you're lowering those dimensions. So if you're doing EDA and you wanted to visualize all of your features as a whole, TSNE is usually the one to go. However, TSNE takes a very, very long time to run because it is looking at the relationships between every single one of your points to increase the separability as much as possible. So as you can see here, it is highly recommended to use another reduction method first and then use TSNE. So maybe if you had like 1,000 features, maybe you lower it down to 50. This is their example. You lower it down to 50 using PCA or truncated SVD, and then throw it into TSNE for your visualizations. Just because it takes very, very long time, because as you can see here, basically converts similarities to joint probabilities and minimizes divergence between probabilities. So basically, it's doing a lot of computation to make sure that you're optimally separable between your classes. Cool. Questions about this? All right. So back to PCA, and actually you can employ the same thing for truncated SVD. This is actually my last slide. In tuning your PCA or truncated SVD, how many principal components is best for your data set? Now, PCA, I think it's fairly important to remember that PCA tries its best to optimize for maintaining the variance in your data. So what you can actually do is out of PCA, one of the attributes that you can get is your explain variance. So explain variance is something that after you fit your PCA or after you fit transform your PCA, you can find out how much of the variance it has retained. So it's usually a number out of, it's a number less than 1, between 0 and 1, because how much percentage of the original variance is maintained after you do your PCA transformation. So usually what you would do, you don't want to lose too much of your variance, but you kind of want to see where is low enough a number of dimensions where, you know, you're still, that you still have enough of the variance. So this is an example graph that you can get from PCA. If you just run your PCA a bunch of times for a different number of components, you can plot the explained variance. And what this is showing, and let's just assume that this data set had like 1,000 features, for example. If it had 1,000 features, by like roughly 45, you're pretty much explaining all of the variance already. So that goes to say that like maybe over like 900 of the features don't have too much meaningful variance. So therefore, you know, going 45 is enough. But maybe you have a certain threshold that you want to at least get, or you want to kind of do a trade-off between maximum number of features and minimum number of features and maximum amount of variance. So maybe you're saying, okay, well, at 20, I still have about 90% of the variance in my data. So maybe I just go with 20. It really depends on your data set and how long your model is taking to run, or it depends on what you're doing your dimensionality reduction for, really. But explain variance curve is pretty important, especially if you want to use PCA as part of your modeling pre-processing steps, just to make sure that you're not losing data. Neither are you doing a lot of redundancy, because redundancy is where if I pick any number greater than 45, those additional dimensions don't really contribute to the variance of my data, right? If I go to like 45 to like 50 or anything above that, I'm already at 100% variance. My model is not going to perform much better. And none of my classification nor regression models are going to perform much better with additional dimensionality. But again, downsides is you do lose that direct interpretability when you use reduced dimensionality data. Cool. So that's PCA. If you did have a lot of features in any of your projects, you can definitely try it out. It is one of the steps that you can incorporate as part of your scikit-learn pipeline if you'd like. But yeah, it's a pretty neat one. I think that for this upcoming project, PCA, or not just PCA, but any of these other methods would be actually really interesting to play around with and take a look, especially for like EDA. I think it's really neat to get like a graph like this just to see like all in all, how is your data separated? Not just for classification, but for regression as well. If you were trying to predict some sort of continuous variable, you can kind of plot like maybe a giant scatter plot of like continuous versus like a one PCA or a single principal component of all of your features. Or you can do something like this, where you have like a gradient of your data points referring to, you know, the range of values of your target variable, and then taking a look to see what the distribution of your features set is like. But yeah, that is PCA and dimensionality reduction. This is something that's kind of optional to incorporate in a lot of machine learning projects. It really helps for visualization and EDA purposes, but also for efficiency. So if you don't feel the need to use it, you don't have to, but it's really good to know that it exists. But sweet, awesome. Any questions at this point? By the way, all of the materials for the rest of this week are already up on our repo. So yeah, just in case anyone follows those, that is there.
Can you go into like a quick overview of the different electives just so we have like an idea of what they all are?
Yeah, absolutely. Actually, yeah, that's a super good idea. Okay, so I would say the electives really begin from like 36 onwards. So today, PCA, I mentioned, like if your project doesn't need it, you don't have to use it. Same with clustering, and big data is kind of like its own thing as well. So the first one would be recommendation systems, and there's a couple different ways that you can do it. But the final project, the data set that is provided for you, actually, I think that's what I'm going to use to like explain each one, the final projects. The recommendation system project for this one is a movie recommendation project. So given a lot of data about users' past interactions and ratings of movies, can you recommend movies for a new user? So that's the project for this one. Not to like bias anybody, but recommendation systems are my personal favorite part of the course. So yeah. Next is time series data, which is basically exploring trends and making and forecasting predictions. So the main difference between time series and anything we've done lately, yes, you're also making predictions, but is specifically forecasting. If I have data up till 2021 in June, my predictions will be for in the future. And so this is very, very tied to time. The chronological order of your data points is very, very important. The project for this one is you're given a bunch of median housing prices for zip codes. And the idea here is you're going to run a bunch of time series models, which you can also automate. And I'll talk about automation when we get there too. You're going to do a bunch of time series modeling for a bunch of different zip codes and recommend which zip codes look to be the most profitable. Next, natural language processing. And natural language processing, the project is actually very, very similar to the last project. It is also a classification project. The main difference with natural language processing is the way that you pre-process your data, because we haven't really talked too much about how we treat text data, aside from what we did in that naive Bayes chapter, where we just made like, a word count matrix. There are a bunch of other pre-processing techniques, which I'm going to talk through, but the end product is also classification for this topic. I believe, I hope it hasn't changed, but it used to be on Twitter data from South by Southwest, and I think it's from like 2012 when like the iPad came out or something like that. And you're supposed to classify whether the tweets are positive, negative, or neutral. So a sentiment analysis, which is actually highly relevant right now. I would say NLP is one of the hottest and fastest growing parts of data science right now, in my opinion. And then finally, it's neural networks, but it's more for image classification. So neural networks is the last part of our curriculum. And I will say that most students, I would say like 90% of our students won't go into neural networks at their first role, because it is quite advanced and you're usually expected to have some experience before getting to neural networks. However, we will set up a framework of how you will use neural networks. And you can see there are 3 topics there. And the project here is your data set is chest x-rays for pneumonia patients, or just chest x-rays, some of which are of pneumonia patients, and you're diagnosing whether a person has pneumonia or not based on their chest x-ray. So that's also a classification problem. The principles of classification still do apply, but that's the data set for that. And yeah, those are the 4 topics. I will say the appendix for this phase is especially important for some of the electives. So for example, the time series appendix, which is only 2 labs, I do think is very, very important. I will talk about those as well. This one for neural networks, I will talk about when we get to it as well. And deep NLP, this is actually what I'm going to talk about, because I do think it's highly relevant right now with all the newer advancements in NLP. So I actually am going to spend a study group talking about the appendix part of NLP. And yeah, the project info is already there if you wanted to take a look. Hope that was helpful. If anyone has any like already, oh, you're welcome, Naomi. If anyone is already like has an idea of what they want to work on, feel free to let me know. Of course, yeah, we don't have the project for another 3 weeks, but yeah, that was a good way of breaking it down, I think. Any other questions about any of the stuff we covered today or about phase 4 in general? All right, once we get to like next week's part of phase 4, I'm going to start really referring to our capstone. I know it's a little bit early, but I do think it is important to start at least thinking of capstone ideas. I'll tell you that capstone, you have to find your own data, and it cannot be a Kaggle data set. So start thinking about what data you can like web scrape or API get. And don't worry, I will be doing like an API web scraping review for you all at the beginning of the capstone phase. And yeah, let's not talk too much about capstones for now, but it's good to be prepared for it because it's going to be in about a month. Neat. Any other questions? All right, well, if there's anything else, feel free to Slack me and let me know. Today's topic was a little bit shorter, but tomorrow is going to be a little bit longer because we're going to talk about 2 main types of clustering algorithms. And then, yeah, we're just going to hit the ground running for the rest of the phase. Don't forget to schedule your project 3 reviews if you haven't already. I do recommend getting that out of the way as soon as you can because we go right into phase 4 and right into capstones after that. So just good to get them out of the way. See, well, if there's nothing else, Slack me if there are any issues with anything, but looking forward to your reviews, and I will see you all tomorrow. All right, bye everybody.